In this video, we will solve the sample problem of an aircraft wing vibration excited by the engine.
Okay, so this next sample problem is on the free and forced vibration of beams. And part A of the question, you're first asked to show that the first and third natural frequencies of a pin-pin beam are orthogonal. So let's have a look at that first. So part A is on orthogonality. And we can state from lectures the orthogonality expression. It's really the test for orthogonality is given by this integral, and we called it a shape integral from the length of the shape of, in this case, a mode y of x, and that can be any mode. We call it sub r, or r could represent any mode, times by, that's the convolution integral, which is a product integral as shown here, where any two modes, the product of it, and we take the integral, and that's our test for orthogonality. So that equals 0 if the modes are orthogonal to each other. In this case, we have a pin-pin beam, and we'll be taking the integral from 0 to L, so all we need to know is the mode shapes for the pin-pin beam. So we want to check that the first mode is orthogonal to the third mode, so we're really just subbing in the mode shapes for y of r and y of s and evaluating this integral and checking if they equal 0. So for a pin-pin beam, we've already evaluated the mode shapes in lectures. So from that we got the mode shapes y of n as a function of x equals c of n sine beta n times x, where beta n equals n pi on the length L. Okay, so really we're just substituting in for n equals 1 and n equals 3 into these two shapes here and evaluating that integral. So as you can see there, we're going to get an integral from L to naught of y1 of x times y third mode of x dx, which equals c1 times c3, so bringing the constants outside, integral from L to naught of sine pi x on L times sine 3 pi x on L. Alright, so we've just substituted in for y of 1 and y of 3, and we need to evaluate this integral here. Now, from your first year maths, you would have learnt how to do this integral, but you can also just look it up in tables. We know that the integral of sine of a of x times sine b of x dx equals sine a minus b x divided by 2a minus b in brackets minus sine a plus b of x divided by 2a plus b. So, now we have all the mathematics tools we need to solve this integral. So when you substitute that solution into our first and third mode shape integrals, we're going to get the integral from L to 0 of y 1x times y 3 of x dx equals C1 C3 outside of sine 2 pi x on L divided by 4 pi on L minus sine 4 pi x on L divided by 8 pi on L. And we evaluate at the integral endpoints from L to 0, and you should find that you've got sine of 0 minus sine of 0 and sine 2 pi and minus sine of 4 pi, and that should equal 0. So therefore y1 of x and y3 of x are orthogonal. Okay, so remember that means that these shapes are completely independent of each other, so they don't pass energy to each other in a linear system. And also, because these shapes are completely independent and orthogonal, we can use them as basic building blocks to represent other shapes, like the forced deflection shape. Which brings us to the next part of this problem, which is part B, which is now we're looking at a cantilevered beam represented by a wing of an aircraft, and it's excited by a transverse harmonic force of frequency 10 times the fundamental natural frequency. So this could be due to an aircraft engine. A slight imbalance in it will always give some excitation. In this case, we're applying it at a point 0.3 of the length from the free end. So we're 30% from the free end, and we're asked to develop an expression for the response amplitude and plot the response deflection shape. Okay, so part B, we're looking at force response of a cantilevered beam. Just fixing up that diagram a bit. We've got a force at a point, we'll call it F naught, sine of 10 times the fundamental frequency, so sine 10 omega 1 t. And it's applied at a point 0.3 times L. All right, so we need to start off looking at the modes of vibration. As we said, in a force vibration analysis, we can make up the force response using contributions from individual modes because they're all orthogonal to each other. So we can start off by looking at the modes of vibration. So the modes are given by, for a cantilevered beam, y of I cos beta I x minus cos beta I x minus C1 outside of sinh beta I x minus sine beta I x. All right. So again, that's straight from your handout. So this is our beam handout, and we can look up for a clamped free beam, which is a cantilever. There's our mode shape equation. We also have our natural frequency, which we need these beta L values. So we look down in this table for a clamped free beam. It gives us our beta L's for each first, second, third and fourth mode, and this constant C1, which we need in this mode shape equation to give us the shape of the modes. Okay, so let's write down what those beta values are. So beta I times L for the cantilevered beam equals 1.875 for the first mode, then 4.694 for the second mode, then 7.855 for the third mode, and then 10.996, and so on. Okay, for the C1 values for the mode shape, we need 0.734 for the first mode, 1.019 for the second mode, 0.999 for the third mode, and 1.000, and so on for the fourth mode. So now we can work out our force beam solution. Once we have the modes, we work out how much each mode is excited. And this is what we did in lectures. It's called a modal participation. And we've worked that out for a point load excitation. And for each mode, A sub I, that's equal to 1 over beta I L to the power of 4 times F L cubed on EI, which is like a static deflection term, so that the stiffer the beam, the smaller the amplitude of the dynamic response. So multiply that. Actually, we'll use the resonance term first. So this gives us a factor depending upon how close the forcing frequency is, which is 10 omega 1 divided by omega I squared, and then we multiply that by the mode shape as well. And we evaluate that at the load point. So again, if you're forcing a system at an anti-node where you have a high response in that mode, that's going to excite that mode a lot. Whereas if you're exciting it at a node point where that mode has no response, you won't be able to excite that mode. So we evaluate the mode shape at the forcing position, which is 0.7 times L, this point here. All right, now we have an expression here for the mode shapes, the beta ILs and the C1, so we can substitute that in and we can evaluate this mode participation, AIs, for each of the modes. And we can start off at 1 and go all the way up to as far as we want. Now, obviously, we've got Koshas and Cinches. This is going to be quite an onerous problem to write down by hand. So typically at this stage, after you calculate the AIs, you can then have a look at a numerical solution. But let's just calculate the AIs first. So they're going to equal, evaluating all those numbers, you get for firstly minus 9.66 by 10 to the minus 4 for the first mode. Then you get minus 8.36 times 10 to the minus 4 for the second mode. And then minus 5 times 10 to the minus 4 for the third mode. And then for the fourth mode, we get 6.22 times 10 to the minus 5. And if you evaluated the fifth mode, you'll find this number gets smaller and smaller. So you can see there's a 10 times smaller contribution between the third mode and the fourth mode. And there's a few reasons for that. Firstly, the frequency is 10 times the first natural frequency. Okay, but you'll see the natural frequency depends on beta IL squared. So our first natural frequency is 1.875 squared. By the time we get to the fourth mode and we square this number close to 11, we're getting a number which is much bigger than 10 times the first mode. So we'll find that this forcing frequency is much smaller than this fourth mode frequency, and that's this resonance term is getting much smaller. We can look at this a bit more closely when we look at the numerical solution, so let's do that. So we'll write down the expression for the deflection amplitude. And it's just going to be equal to y of x as a summation of all the modes, which is expressed as a summation of the AIs times YIs. So with this modal participation, you need to multiply that by the mode shape again. And you can evaluate this mode shape at the point you're measuring the deflection. In this case, we just want to measure all the way along the beam, so we'll leave this yi as a function of x. We can use MATLAB to evaluate. We'll say for the first 4 modes. And they're plotted over here. So what have we plotted here? We've plotted versus position x on the length of the beam, and we've plotted the y of x. And we don't know the geometry of the beam, the EI on L cubed, and we don't know F naught. So we'll divide our solution by F naught L cubed on EI. And we'll also plot the contributions to that y of x. So I'll just put a comma representing the fact that the thinner lines here referred to each of the contributions from each of the modes. So we have the first mode, A1 times Y1, shown there. You can see that first mode shape there, and it contributes a lot in terms of the deflection, particularly at the end of the beam. The second mode we've got coming down and then up. So that's A2, Y2. And you can see it's got a node point, which is around about 0.2. The forcing is about here, so the second mode isn't perhaps excited as much as we'd expect, and based on the frequency, and the reason for that is that the forcing point is quite close to a node point. The third mode has two node points, so it goes down, up and down. And that's the one seen here. And finally, we have the fourth mode contribution shown there. And all these add up to give us our y of x, which is the summation of all of them. So you can see evidence of sort of a third mode, which is distorted upwards, perhaps due to the second mode, and the first mode shape. So our final forced vibration shape is given by this shape here. Okay, so there you've seen how to calculate the force vibration response of a transverse vibration of a beam as a summation of individual mode contributions. And just a small correction here. Note that as the modal frequency moves further and further away, so typically the higher modes from the forcing frequency, we get a smaller and smaller response, so that we can fairly accurately approximate the full force deflection amplitude by using only a small number of modes. And that's the power of modal analysis. We've basically simplified an infinite degree of freedom system down to a small number of degrees of freedom.
In this video, we solved the sample problem of an aircraft wing vibration excited by the engine. We solved for the forced vibration response shape and showed the modal contributions are dependent upon how closely the forcing frequency matches the natural frequencies, the static deflection of the wing, how high the mode is, and the position of the engine.